At 10 o'clock in the morning on November 7th, 1940, Leonard Coatsworth drove onto a bridge. He was a copy editor at a local newspaper. He had his daughter's dog with him, a three-legged cocker spaniel named Tubby. He was heading to the family's summer cottage on the far side of the Tacoma Narrows Strait. He had crossed this bridge dozens of times. It always moved a little. Everyone knew that. The construction workers had given it a nickname because of it. They called it Galloping Gertie. But today was different. Today it wasn't just bouncing up and down, it was twisting. The left side of the road rising as the right side dropped, then reversing. A slow, rolling torsion, like a ribbon being wrung out by invisible hands. Coatsworth stopped his car. He tried to walk. He couldn't stand upright. He got on his hands and knees and crawled to the edge of the bridge. He left Tubby in the car. At 11:02 a.m., the first large section of the bridge fell into Puget Sound. By 11:10, it was over. The car, and Tubby, went with it, and the world's most advanced suspension bridge became the most famous engineering failure in history. This is the Failure Archive, and this is the story of Galloping Gertie, how it was built, why it failed, and what it changed forever. To understand why the Tacoma Narrows Bridge collapsed, you have to understand the man who designed it. His name was Leon Moisseiff, and in 1938 he was one of the most respected bridge engineers in the world. He had worked on the Manhattan Bridge. He had consulted on the Golden Gate. He was, by any measure, at the top of his field. And he had a theory. Moisseiff believed that bridges should be flexible, that they should move with wind forces rather than resist them. He developed what was called the deflection theory, a mathematical model that predicted how a bridge deck would deflect under load. His calculations showed that a very slender, shallow deck could handle the forces at Tacoma Narrows. The numbers worked. What the numbers didn't capture, what nobody had fully thought through yet, was what happens when a bridge deck stops behaving like a road and starts behaving like a wing. Here's the detail that changed everything. Most suspension bridges of that era used open steel trusses for their decks, frameworks of crisscrossed steel that let wind pass through. Moisseiff's design used solid plate girders, 8 feet tall, continuous along the length of the bridge, smooth and flat. In theory, this made the bridge more elegant, streamlined, modern. In practice, it made the deck behave like an airfoil, like the wing of a plane. Wind didn't pass through it. It was forced up and over the top, and down and under the bottom, and that created lift. The bridge opened on July 1st, 1940. It was the third longest suspension bridge in the world. Local dignitaries gave speeches. Traffic flowed, and the bridge moved. From the very first day, in any moderate wind, the deck would oscillate vertically, rising and falling in slow rolling waves. It wasn't dangerous, engineers said. It was within design tolerances. The bridge was supposed to be flexible, but it was strange enough that construction workers had noticed it during building. They called it Galloping Gertie, and the name stuck. Local people would drive across it for the novelty of it. Some reported feeling seasick, some loved it. Engineers were watching. The University of Washington was hired to study it. A professor named F. Bert Farquharson ran wind tunnel tests on a scale model. He found something troubling. Under certain wind conditions, the bridge didn't just oscillate. It could enter a torsional mode. Instead of the whole deck rising and falling together, one side would rise as the other fell. A twisting motion, much more violent, much harder to stop. Farquharson's team recommended fixes. In October 1940, temporary tie-down cables were installed. Steel wires anchored to the deck and the ground meant to dampen the movement. On November 1st, 6 days before the collapse. One of those cables snapped in a high wind. Repairs were underway. They ran out of time. November 7th, 1940. Early morning. Strong winds push through the Narrows from the southwest. By 7 a.m., the bridge is oscillating. By 10 a.m., the motion is bad enough that the bridge is closed to traffic. Leonard Coatsworth is already on it when it closes. Professor Farquharson is there too, on the bridge, filming with a movie camera, trying to document the oscillations for his research. He later said he believed the bridge would survive. He had seen it move like this before. But at around 10 a.m., something changes. The oscillation mode shifts. The bridge stops bouncing vertically, uniformly, both sides together, and begins to twist. The torsional mode Farquharson had identified in his wind tunnel tests. The mode the tie-down cables were supposed to prevent. One side of the deck rises, the other falls. Then they switch. The amplitude grows. At maximum, the roadway is tilting 45 degrees to either side, a 28-foot difference in height between the two edges of the road. Farquharson attempts to rescue Tubby, Coatsworth's dog, still in the abandoned car. Tubby bites him and retreats under the seat. At 11:02 a.m., a 600-foot section of the center span breaks free and falls. It hits the water with a sound witnesses described as a cannon shot. More sections follow. The collapse runs outward from the center like a zipper unzipping. At 11:10, just 8 minutes after the first section fell, it is over. Coatsworth's car, Tubby, 5,000 tons of steel and concrete, at the bottom of Puget Sound. For decades, the Tacoma Narrows collapse was taught in physics classes as a textbook example of resonance, the idea that the wind was oscillating at a frequency that matched the bridge's natural frequency, like pushing a child on a swing in rhythm until it flies too high. That explanation is clean, intuitive, easy to teach. It's also not quite right. The actual cause is more complex and more interesting. It's called aeroelastic flutter. Here's what happens. Wind hits the solid deck. Because the deck is shaped like a wing, it creates lift, an upward force on one side. That lifts the deck slightly, but lifting the deck changes the angle it presents to the wind, which changes the lift force, which changes the deck angle again. It's a feedback loop. The bridge's own movement changes the aerodynamic forces acting on it, which drive more movement, which changes the forces further. The energy doesn't dissipate, it builds. Given enough time and the right wind speed, this loop becomes self-sustaining. The bridge feeds energy into its own oscillation, and no structure can survive that indefinitely. The Tacoma Narrows collapse rewrote bridge engineering. Within years, wind tunnel testing became standard practice for every major bridge design. The concept of aeroelastic stability entered the engineering lexicon permanently. Every suspension bridge built since, the Golden Gate retrofit, the Severn Bridge, the Humber Bridge, was designed with aerodynamics explicitly in mind. Leon Moisseiff never designed another major bridge. He died in 1943, professionally ruined. Farquharson, the professor who filmed the collapse, spent years studying the wreckage and the aerodynamics. His work directly contributed to the new engineering standards. A replacement Tacoma Narrows Bridge opened in 1950, built on the same tower pedestals, but with an open truss deck that lets wind pass through. It is still standing. The original bridge, Galloping Gertie, is still at the bottom of Puget Sound. It was declared a National Historic Place to protect it from salvagers. It is now one of the largest artificial reefs in the world. What's striking about the Tacoma Narrows collapse isn't the destruction. It's the confidence that preceded it. Moisseiff's calculations were correct, as far as they went. The engineers who approved the design were competent. The people who declared it safe were not reckless. They simply didn't know what they didn't know. That's how most engineering disasters work. Not incompetence, not negligence, a gap between what the models accounted for and what the real world contained. The bridge lasted 4 months. The lesson lasted forever. This is the Failure Archives.